we have learned how to use the mathematical induction to prove an equation is an identity. And there we studied with n equals 1. And here this one is different. To ask us to prove 2 to the n plus 1 is greater than 4 times n, this one inequality, not identity or equation. Inequality is true for n is greater than or equal to 4. This one may not be true for 1, 2, 3. When n equals 1, 2, 3. Okay, so that's new thing. Now, we first need to note is that, first, note the inequality is not true for n equals 1, 2, 3. Why? You want to look at this table. See the table right here. The left-hand side is 2 to the n plus 1. The right-hand side is 4n. When n equals 1, 2 to the first plus 1 is 3. Okay, 2 to the first is 2. But 4 times 1 is 4. So left-hand side is actually less than right-hand side. Remember here is greater than. So this inequality is not true for n equals 1. When n equals 2, you can do the same. So when n is 2, 2 squared plus 1 is 5, but 4 times 2 is 8. Again, 5 is less than 8. So this inequality left-hand side greater than right-hand side fails when n is 2. Okay. Similarly, you can see when n equals 3, that's 2 cubed plus 1. 2 cubed plus 1, 2 cubed is 8, plus 1 is 9. Okay. And right-hand side is 4 times 3 is 12. 9 less than 12, so left-hand side is less than right-hand side, is not greater than when n is 3. So for n equals 1 to 3, this inequality is not true. Starting with 4 is going to be correct. And here is the proof. The inequality is true for n equals 4. You may try it. Okay, you plug in 4 here. 2 to the 4th is 16. Okay, and the 16 plus 1 is 17. Now, right-hand side is 4 times 4, which is 16. Of course, 17 is greater than 16. So this inequality is true for n equals 4. Now, then we may assume this inequality is true for k, where k is greater than or equal to 4, because k can at least choose what? Choose 4, not 1, 2, 3. Starting with 4. Okay? Yeah. So k can at least choose 4 in our mind. Now, that means if we assume this one is true for n equals k, so we may replace n with k. So 2 to the k plus 1 is greater than 4k. It's true for k greater than or equal to 4. Now we want to do is, this one is also true for k, for n equals k plus 1. Okay? Before we do that, we want to note that when k is greater than or equal to 4, when k is greater than or equal to 4, then 2 to the k is greater than or equal to 2 to the 4, because k is greater than 4, okay? That's important. And then 2 to the 4th is 16. 16 is greater than 4. So when k is greater than 4, we want to understand is 2 to the k is actually greater than 4. That's one thing we want to be clear in our mind. Okay? Another thing is that starting with this one, we want to prove this one is also true for k plus 1. Okay? One needs to show is that replace this n with k plus 1 will be like that. Okay? It was n now replaced by k plus 1. It was n now replaced by k plus 1. Okay? We want to show this is true. Show means we want to prove this is true under this condition. Because we assumed this is true. Assume this is true. So starting with n equals k, we want to prove the inequality is also true for n equals k plus 1. Yeah, we want to show it does not mean here this is already true. We only assume this is true. We have not proved that this is true yet. We want to show this is true, starting with the given condition and k equals 4, greater than or equal to 4. Okay, this is the thing I want to put a note because I will use that. Now, if you look at the left-hand side, which is 2 to the k plus 1, then you can rewrite 2 to the k plus 1 as 2 times 2 to the k. Because of what? Because 1 plus k is k plus 1. Base 2, base 2, those two are the same. So you can add exponent. And then you know 2 times 2 to the k is actually 2 to the k plus 2 to the k. 1, you just keep writing it. You just keep it. Okay, 1, 1, 1. Why this is true again? 1 times 2 to the k is 2 to the k. 1 times 2 to the k is 2 to the k. You pour 2 to the k out, 1 plus 1, you got that. Okay, you got 2 times 2 to the k. Okay, that's the reason this one equals that. Now, look at this one. 2 to the k plus 1, right here is greater than 4k. So this thing is actually greater than 4k. And previously, we also note 2 to the k is greater than 4. You see where? 2 to the k is greater than 4. So the left-hand side, this 10 greater than that, this 10, 2 tens together greater than that by assumption. This is what we have noticed because k is greater than 4. So this quantity actually greater than this quantity. But this quantity, when you pour 4 out, because 4 again is 4 times 1. You pour 4 out, you have k plus 1. And then this actually tells us 2 to the k plus 1, and then plus 1 is greater than, right here, 4 times k plus 1. So look, this is what you want to get, and this is actually the proof. You see, 2 to the k plus 1 is the one here, and the right-hand side end up with this. So you have a proof that this is true by starting with 2 to the k plus 1 greater than 4k with the condition k greater than or equal to 4. So then you can conclude that the inequality is true for n equals k plus 1. Means this is true for n equals k plus 1, where k is greater than or equal to 4. All right. Now, what can you conclude? You assume this inequality is true for n equals 4. And then you assume this is true for k because k at least can choose 4. And then you have proved through here that and this inequality is true for k plus 1. So it tells us if k is 4, k plus 1 is 5, we'll make this one be true. And then again, this loop will never end. Okay? And then, you put it back, k can now choose 4 and 5. You go through this process again, you can show n can be 6, because k plus 1, when k is 5, n will be 6. Then this is going to be true for 4, 5, 6. You do the same process, you'll get n can be 7. So this loop, again, never ends. Then you can say that, hence, due to n plus 1 greater than 4n is true for n greater than or equal to 4. As long as n is greater than or equal to 4, you can claim that's true. Okay? Yeah, even for 100, when n equals 100, 1000. All right? Okay, I'll see you next time.